Okay, for this section, I will introduce two topics. One is sign extension, the other is one-hot decoder. Okay, for sign extension, please see the code segment here. What is sign extension? That is, you want to extend the sign bit of a value, of a signed value. If the designer think A is a signed value, that is in the two's complement format. Okay, two's complement format. So the bit 15 is the sign bit of this value, and you want to extend the sign bit and keep the value represented by this variable and the original variable the same. So this is called a sign extension. For a single example, for 4-bit example, if you have a 4-bit of 1, okay, this is sign bit, you can extend it. Yes, the value is also 1. And for the -1, this is -1. Yes, in the two's complement format, if you extend the sign bit of 1, this is also -1. Yes, in the two's complement format. But if you do 0, extension, the value will be changed. Yes, change from -1 to 15. Yes. Okay. So for sign extension, you just put more bits of the sign bit and the most significant bits. So you can put 1 bit is okay. Okay. Use this symbol to concat bit to join the bit segment. Or if you want to repeat the same bit segment for several times, so you can write it in this format. This is repeat this bit segment for 2 times. So this will give you 2 bits of, this is equal to 2 bits of A15. Yes, so this 2 bits and 16, so yield 18 bits. This is 18 bits. So this is called sign extension. Okay. And sign extension is usually used in the arithmetic operation, that is add sub for signed number. Okay, please see the code segment here. Can you understand the meaning of this code and the function of this code? Yes, they are the same. Yeah. So can you draw the block diagram, the circuit diagram of this code segment? Yeah. A, B, C, and together. Okay. So what is this say? This has been explained in the part 1 of this course. Arithmetic database segment section. Arithmetic database section. Okay. So for this segment, you can say we do 0 extension. Yes, we do 0 extension for the value C. So most likely C is an unsigned number. Yes, most likely. Okay, most likely we can expect that most likely C is an unsigned number in the view of designer. Okay. And please note that for the always procedure block, the how to write the sensitive list. There is two methods to write the sensitive list. Okay, you can list all the signals here, list all the input, or you can say the trigger signal here, and you can just put a star here. Okay, this is the preferred. I prefer this coding style. Simple and won't introduce any mistake. Okay. Okay, let's say the difference of sign extension and zero extension for the arithmetic calculation. So let's assume A and B are signed number. In the view of designer, we treat it as signed number in the 2's complement format. Okay, and we want to do the operation of A sub B. So you can say you may write it in this format and in this format. For the first one, we do sign extension. Okay. For the second one, we just write A sub B, and by default, the tool will think in the view of EDA tools such as the simulator, the synthesizer tool, or the Verilog syntax. The tool will treat it as unsigned number. So it will do zero extension, and do the sub operation. And you can imagine the result of out 0 and out 1 is the same a lot. Okay, this is the test sequence you can try. For example, you can try A equal to 1 and B equal to 1, and use sign extension and zero extension to do the calculation, and to see the final result of 17 bits. Then you can change B to 60 bits of FFF, that is -1. Yeah. Then you can use the tool to do the calculation, and you can say what's it, and you can say the difference of the two expressions. For the second test case, after extension, this is the value, AB value after sign extension, and this is the value after zero extension. So you can try it. You can take out a pen and a paper and do the sub operation by your hand, or you can write the code and simulate it. Okay, this is an example of the difference for signed number in arithmetic calculation. You have to, if the designer treats the number as signed number, you have to sign extension by your hand. Okay, you have to do sign extension by your own. Can't rely on the tool to do the zero extension. Okay. And the other way to coding this is you can use the signed keywords here, and you'd better also name the result is signed. Okay, you can use the signed keywords, then you can write it in this format. This will give you the right result. This is because you have tell the tool they are signed number, and when do calculation, the tool will do sign extension for you. Okay. So for the signed keyword works, the suggestion is all the operand at the left side and the result at the left side. Sorry, all the operand at the right side and the result at the left side will be defined as signed value. Okay, or we'll use the keyword signed. Then this will give you the correct result. And please note that, let me show you an example. Okay, if you have, even you have defined, okay, even you have defined it as signed number, if you just select some bits, okay, select some bits of this signed number, this will be converted to unsigned by the tool. So if you want to use it, sorry, okay, let's just write it in a simple code. Okay, let's give you some example. Okay, let's ignore the bitwise. That should be okay. Okay, we have defined sum and sign, but we just select some bits of it. This will, so the tool will treat this operand as unsigned, this as unsigned. So if you don't want to do sign extension for it, you can use the system task signed. Yes, you can use this. Okay, you can use the signed system task and change this value, change the value to signed. Oh, let's check. Okay, let's make sure the keyword I use is right. Just check it. Okay, it's right. Okay, there is also, you can say it will return the value is signed. Okay, there is also unsigned system task. The two system tasks are synthesizable. Okay, and if you join some bits, okay, this will cause the return value unsigned. Even if you have defined sum and signed, then you can also put a signed keywords. You can also put a signed keyword here and call the signed system function and change the value to signed. Okay. Okay. Okay, that's all I want to talk about for sign extension. So for beginner, you may confuse now. Okay, what's the value of for a 4-bit binary? What's the value of this binary in the 4-bit? What's the value? So it can be explained as 15 if you treat it as unsigned number, and it can be explained as -1 if you treat it as signed number. So what's the value of these bits It depends on how you treat it. How you treat it, there is two defined. They defined by Verilog tool and they defined by designer. From the tool we use, they will check the variable or the signal defined. When you define it signed or unsigned. Yes. Okay, this is something confused. You have to figure it out and make it clean. From the designer view, okay, even I define a unsigned variable or unsigned signal, I can put signed value to it. Yes. As signed, unsigned, they are just binary values. Okay, this signal can hold binary values. Okay, how to explain it depends on how you use it in the code. Okay, this must be confused for beginner. Okay, you have to, when you make some mistake, you will make it clean. Okay, let's go on for one-hot decoder. What is one-hot decoder? That is you have a signal such as cell. Okay, cell is one hot, and you want to decode some information from the input cell. Cell is one hot. So one hot, I have explained in this. Yes, one hot. For all the bits in this signal, only and only one. There is one and only one bit equal to 1. All the other bits are 0. Only 1. Yeah, this is called one hot. So how to decode this? For example, if the bit 0 is 1, I want to output this value to D out. If bit 1 is 1, I want to put this value to D out. So how to code this function? Yeah, this is a method of coding it. Use the case statement, and this is a check value. The check value is a constant one. Yes, we will check whether this bit is equal to 1 or not, whether this bit is equal to 1 or not, whether this bit is equal to 1 or not, and whether this bit is equal to 1 or not. If this bit equal to 1, and this statement will be executed. Okay, this put constant here may be strange for you. Okay, so you have learned something new here. You can put constant and the case compare value. And we have said that to make sure this will generate a compilation logic, the designer must make sure the match item is complete. Yes, is complete. That is, every time this block is triggered, out will be assigned a value. Yes, it can't hold the last value. So, is the first statement complete or not? Is the for compare item complete or not? Is there any case this always block is triggered and none of the item match from the view of tool? Yes, there is. The tool will think you may have cell equal to 0, 0, 0, 0. Yes, in this case, none of the match item will match. So out will keep the last value. Yes. So this will generate this. So the tool will think this statement is not complete, and it will use latch and some combination logic to implement it. So this is not what we want. How to avoid this? You have to use the synthesize directive. Okay, you use the synthesize directive. You use the synthesize directive to tell the tool that this is complete full case. Yes, you use full case to tell tool that you must treat it as a complete case. That is, you tell tool the designer can make sure each trigger there will be one item matches the match value. So the tool will treat it as a complete case statement. And can the tool infer there is only one match item can match? No, because the tool may think you may have the value that equal to this. Then there will be 3. Yes, there will be 3 item match, and in the view of tool, this will have the higher priority. If the designer can make sure there is just one bit at any time, you can tell your tool parallel case. That is, you tell your tool, the designer tell your tool only one item can match at each time. So the tool will use the Mux architecture to implement this code. Okay. 2 important points. Synthesize directive. Okay. This is a keyword. And you write it after the case keyword as a comment. And you have noticed that why the keyword is Synopsys, the name of an EDA tool or company. Yeah, this is because maybe it's Synopsys first invent this directive. Okay. Okay, the second is you can put a constant in the match value. And whether you write default, yes, whether you write default match item here, it's okay. Okay, you write it or you not write it, it's both okay. And let's check whether the full case directive has added to the Verilog standard or not. Okay, it seems it's not. Okay, seems the answer is no. Okay, not added to this Verilog standard. So the problem is if you use some other synthesizer tools, such as tools from Sinis or from Atara or Intel or a synthesis tool from Cadence, you'd better to check the manual. Okay, for full case and parallel case, how to write this keyword. Maybe they will use Synopsys, or maybe they will use synthesis. Okay, you have to check the manual. But for design compiler from Synopsys, Okay, synopsis. This syntax is okay. Okay, this is the one method to code one hot decoder. So the full case is a must, and parallel case is better. If you miss parallel case, it will generate to synthesize to compilation logic, but this will give you the priority mux architecture. Okay, not parallel mux. That is, you will get something like if else, if else, if else, if. The mux are cascaded together. Okay. So the next method to code one hot decoder is code the hardware architecture directly. That is, you write the hardware architecture in your code. So this is the architecture with the same function. Okay, in this time, the output value is multi-bit, not just single bit. Okay, the output value is 7-bit. So the function is extend this select bit from 1 bit to 7 bit. Yes, and it with the input. Then all of them together to generate the output. So you can test if the function is exactly the same. That is, the function is when bit 0 of cell is 1, the output will be D0. Yeah. When this is 0, sorry, when this is 1 and this is 0, 1 hot, D0 will be output. When this is 0, 0, 1, 0, this will be output 2. Yeah. Okay. So this is the second way to code one hot. In this way, there is no need for you to write the synthesize directive. Okay. The third method is use case X or case Z. This is something like the case statement we have used before. So in this format, you write this select signal here as the usage, but the keyword is case X or case Z. Then you just list the 1 hot bit here and put all other bits as X. So this tells to that these bits are don't care bit. Okay, it can match any value. This bit X will match any value in the same bit of select. So that means don't care. Okay, you just check first bit. For this statement, that is, you just need to check this second, third, the last bit. Yeah. So for this case, the EDA tool also count infer. This is a full case, and it also count infer. This is a parallel case. Yes, this is the same. The tool may think cell may be some value like, yeah, can't match either of them. None of them will match, so not full case. And tool may think the cell may be some value like, yes, so the two will match, two matches. So not only one match. So for the same reason, you have to use the synopsis directive. You have to use the synthesize directive. Okay. To tell tool, actually, the designer had to make sure this is a cell is 1 hot encoding, so this will be full case and parallel case. Okay. Okay. One more point for 1 hot decoder. So if the 1 hot input equal to 0 or 0, how to code it? Yeah, if equal to 0, there is maybe 2 situations. One situation is you don't care the output when the value is 0, when cell is 0. Just code this function like this. These 3 slides I have shown you. And the second case is you do care the output value when cell is 0. Yes. So you have to, for this case, you have to write the match item here. Yeah. Yes. And assign the value you want to the out. Yes. You just write the match item here and assign the out to the value you want. And this will also keep, you will also keep this directive. So for this coding, if cell equals to 0, the output will be 0. Yeah, output will be 0. And for this, you have to write a default. For this, you have to write a default. Yes. You have to write a default, then assign a value to out. This is okay. Then if you have write the default, you can omit the full case. Just write parallel case is okay. Okay, that's all for this section. Thanks. You can try it. Okay, you can try it. You can write this code and try it in this simulation. Okay. For 100 decoder, I prefer this coding. This coding is I preferred, and this coding is also okay. So for complex design, this coding may be simple. Okay. And try to use the case Z or case X statement. Okay.